Nice. Okay, so what other questions do we have from the calculator multiple choice from yesterday? Thomas. 92? 88? 90? Okay, 88, 90, 92, any more? 89. Okay, let's start with 88, going to 89, and then we'll work our way through. So number 88, oops. As soon as I see radius decreasing, I'm thinking that there's a derivative, right? I see radius decreasing, and I'm just right now not even looking at the answer key. I'm just translating. Radius of a sphere is decreasing at a rate of 2 centimeters is radius per second is time. Right away I can say, oh sweet, dr dt is equal to, why am I going to put a negative, guys? Decreasing. Rate, derivative, radius, dr, with respect to time over dt, is equals decreasing, negative 2. At the instant when the radius of the sphere is 3 centimeters, such that r equals 3, they're just telling me what to plug in. What is the rate of change, derivative of, I'm guessing with respect to t, but let's figure out what we should put in our box. D of who? The rate of change in square centimeters of the surface area. The area of the sphere. And then they tell us an actual equation for surface area, so forget that. They're saying call the surface area S, and they're giving me an equation for it. So I need to find ds dt when r equals 3 given dr dt. Guys, what do I do to this guy in order to get dt's in there? Oh, take the derivative. Call a related rates problem in your cheat sheet. Are there related rates examples? Yes, there's a ladder falling. Remember the calculus in 20 minutes guy? There's a ladder falling in your cheat sheet. And I think there's one other. I think there are 2 related rates examples. But taking the derivative real fast, we end up with ds dt is equal to 4 pi are both constants. So 2 comes down, and then I get r to the 1, and then I get dr dt. All I have to do is plug and chug negative 2, solve, and I get number 89. Is a bit of a concept-y one. Period 6 asked this one yesterday. We got just a little bit further than you. What does this look like? Especially seeing this. Is there a forever card that says something about f of a equaling f of b, and if so, then f prime of c is equal to 0? It's on the MVT card. It's rolls. It's rolls. So they say, hey, f of a is equal to f of b, and you're like, sweet, therefore, f prime of c equals 0. Sweet, except they said that is not true. What? No. If f of a equals f of b, then f prime of c equals 0. That's true. Hold on. When you see, you think. Isn't there a Rolle's theorem category, right? If I was to go over here really quickly, and I was to go down, and I was to go see, even in the solutions, Rolle's theorem. Here it is. What are the conditions for Rolle's theorem? F of a equals f of b, then f prime of c has to equal 0. But what came before? Continuous and differentiable. What does this problem not say? So if for any reason f prime of c is not 0, or it's not possible to happen, something must have failed, and continuity didn't fail, therefore differentiability had to fail. Well, if differentiability failed, which of these is saying the derivative does not exist? Differentiability had to fail. Otherwise, it would have been guaranteed by Rolle's. All right, number 90. If you guys look at the percentages, that's one of the ones that we start as being one of the hardest. There are a few different ways of looking at this, but let me just pull out hopefully what you guys would have seen. And then let's see if that's enough. Okay, we're used to saying f is concave down whenever we see the second derivative being negative. But if you go on your forever card, who has their forever cards? Can you go to the concavity card? Go to the concavity. We don't bring our forever cards to class? Oh, you're killing me, Smalls. Only 2, 3? My 3, I'm very proud of you. My 4, go to concavity. My 5, there we go. Now we have a few more. Go to concavity card, the concavity test. We have the signs of the second derivative. We have the concavity of f, but who else is on that card? F prime. What's f prime doing if f double prime is negative or f is concave down? F prime is decreasing, which means the rates or the slopes are decreasing, which means as I go from 2 to 4, the rise over run for a concave down, the rise over run is getting smaller and smaller and smaller. The increase between points is getting smaller and smaller and smaller. And increase, why am I saying increasing? Well, because f prime of 3 is 2. So not only do I know that the rate or the slope at 3 is 2, but I also know that f seems to be increasing because this first derivative value is positive. Okay, so f seems to be increasing, which if you guys look at all of these, the y values are going up for every single table. That doesn't really help me. If something was going down, I would probably eliminate it. But I need to look at how it's going up and how much it's going up. At 3, the rate is 2, and the rate is continually decreasing on the entire interval, which means before 3, shouldn't the slope have been more than 2, or the increase more than 2? And then after 3, shouldn't the increase be less than 2? Which table shows that? This one shows an average rate between 2 and 3 of 2. That doesn't make sense. It didn't get to 2 until 3. So how could it on average be 2 if it doesn't even get to 2 until here? That one doesn't make sense. Same here. There's a change of 2 on average over this whole interval. It didn't get to 2 until 3. That doesn't make sense. You can think MBT, average has to equal an instantaneous in between. It didn't hit 2 until 3. Shouldn't have been an average of 2 before. This one has an average of 5, an average of 2.5. This one has an average of 1.5. Wait a minute, 1.5. If you guys are a little confused as to what I mean by average, I'm taking f of b minus f of a all over b minus a. Or a rise over run, I'm going up 1.5 over 1. Should my slope or should my rate before 3 have been lower than 2? No, because it's decreasing. Shouldn't it have been higher than 2? That one doesn't make sense. Both of these have a rate higher than 2 on average before 3, which seems to make sense with a rate of 2 at 3, and it's decreasing, which means it should have been higher before. Now we have to look at after 3. What should happen to the rate as I move past 3? It should get smaller. So before is 2.5, before is 2.5, after is 1.5, after is 2. Which one makes sense? Only letter A. Bigger than 2 before, smaller than 2 after. All based on f prime decreasing. All based on f prime decreasing. Tricky question for sure. I'm not saying it's not tricky, but it is possible. And then I heard 92, which is a bit of a beast because it has to do with density. Number 92. I'm going to use units as my key to solving this problem. I'm going to use units as my key to solving this problem. It might not get the entire idea down for you guys today, but hopefully it'll kind of help. Hey guys, when we integrate acceleration, what do we get? Velocity. What are the units for acceleration? Aren't they like feet per second squared-ish? And if that was my acceleration, what would the units of my velocity be? When you integrate, you're going from a derivative, from a rate, backwards. You're taking away one of the rates in a very loose and imprecise way. But in a sense, you are multiplying by seconds. Or you're multiplying by the denominator. And then if I integrate velocity, I get position. And position has what as a unit? Feet. So then once again, I lose another per second. Okay, we're going to use that here. Because they tell me something about density. They say the population density of a city at any point along a strip X miles from the river's edge. So here's the river, and we're going whatever, X. We could go 0.5, we could go 1, we could go 2, we could go 3, 4, and then at 4 we're done with the city. But the population density is f of x persons per square mile. So we have persons per square mile. Do you guys see why I related it to acceleration? Unit per square unit. Which of the following expressions gives the population of the city? What units do they want if they want population? Persons, right? People? I'm just using persons because they used it there. Whatever. Okay, fine. Persons. They want how many people? The population. I don't care about the per miles anymore. So there's a few different ways of looking at it. There's a few different ways of looking at it. One way, and I don't really like their explanation, I think it's confusing. One way is just strictly to think integration in units. How can I go from persons per mile squared backwards? At all, I have to take an integral, right? So I could take an integral of f of x. Hold on, x bounds. Well, x is how far away from the river's edge, so 0 to 4. That's just the horizontal distance. So I go 0 to 4 dx. But what would this give me? What units would I have if I'm integrating persons per square mile? Persons per mile. Is persons per mile what I want? No. So just integrating, whatever the bounds are, just integrating doesn't make sense. Now, are any of others of these just integrating? Okay. Just integrating, that gets me persons per mile. That doesn't help me with what I need. I mean, it gets me one step closer, but not all the way. So if we were just thinking about units and just thinking about, okay, an integral will get me back one step. I need to go back one more. Which of these would make sense if I was just thinking dimensional analysis? Could I multiply by 4 miles and get to persons? Yes, but would it be right? Could I multiply by 28? Wait, 28, how'd they get that number? Miles squared. Do I want to multiply this by miles squared to get persons? No, okay, that doesn't make sense. I don't want miles squared. And this one's multiplying by miles. Just dimensional analysis, I've narrowed it down to these two. Why could we, just looking at these two, based on what's legal and illegal in an integral, why should I cancel this one out? Who's x? Yeah, good. The bounds. Who's x? Isn't it how far away from the river's edge? If it's in terms of x, I'm not going 0 to 7. That's like y bounds in a dx integral. It doesn't even make sense. So just thinking about units, we can get to b. We could go a little deeper into the idea and being like, okay, hold on, we need to figure out persons. We know persons per square mile. We know what the density is, or at least an expression for density. But if I was just to take this density and multiply it by 4 miles, I could figure out how many people live in this two-dimensional sliver, which is awkward because do they actually live in a two-dimensional sliver? No. But I could think about, okay, from 0 to 4, which way do I want to do this? The density is an accumulation horizontally. So it tells me how people or how many people are living where in a horizontal fashion, moving horizontally, but somehow in some shape or form, I have to translate that to 7 miles in order to get or to cover the entire area of the city. But I can't just say times 4 times 7. I can't just say persons per square mile times 28. That wouldn't work because of the idea of an integral in that this is constantly changing. When x is 1/2, it's one value. When x is 1, it's another value. When x is 1.9, it's another value. So maybe it's something where property near the riverfront is really expensive, and so not as many people live there. A lot more people live far away because it's cheaper. There are different reasons as to why more people would live here than here than here than here. But I can't just say, oh, it's a constant density multiplied by 28. I have to actually use integration to say, no, the density is always changing. So I have to take my integral from 0 to 4 so it considers every single point in between, but somehow I still need to say, I need square miles though. So you're considering horizontally what's going on at each horizontal sliver, but we still have to multiply it by the 7 at the end to get that consideration drawn through that accumulation for the 4 miles, but also for the depth of the 7 miles of the sea. So it's a hard idea. Density kind of has to do with accumulation. We might try to look at a couple more of those before the actual AP. It's a problem that is rarely on the actual AP, but it does show up every now and then. So it's the idea of density / accumulation. If you want to, in your note colored pen, you might want to write down a question mark, especially those of you that are like, I like to understand every single question. That might be something you want to study up on. Density / accumulation in AP calculus. Okay? Let's go back, though, to, oh, sorry, it's the same answer key. Lo siento. The beginning. Let's go back to the beginning. Non-calculator. Non-calculator. You didn't have to know about intersections or finding zeros on your calculator or solving with the derivative function or the integral function. It was all to be done by hand. It was all to be done by hand. So, let me know. Where do you want me to go? What's the earliest question we have? 4? 1? Number 1, what do we do with any limit? Plug it in, plug it, oh, it's infinity. Hey, when you see, you think, isn't there something about limits to infinity? Don't we do degree tests? There's a few different ways of doing it. You could try plugging in, plugging in, plugging in, or you could do degree tests. Now, guys, they wasted so much time foiling. How could you have saved time? Don't we only have to look at the strongest dudes? Isn't the strongest dude on top going to be the x squared guy? 2x squared. Strongest guy on the bottom? 1x squared. But wait, was it a 2x squared or a negative 2x squared? Ooh, okay, negative 2x squared over positive 2x squared. Degree test, ratio of leading coefficients. They're tied, negative 2. Number, oh, you guys made that. Please tell me you did not use ln. Come on, x to the negative 2, that was power rule all day long. What would have made an ln if it was a 1 over u or a 1 over x, right? But you saw them. They were begging you to think ln. Little stinkers. Okay, but AJ, you said number 4, yeah? Did you forget about chain rule? Yep. What do we do anytime we see an integral? Just mental. That comes from a cosine. That comes from a sine. No, don't you dare. We always think u sub. You guys say it. What do we think? What do we think? Why? Who's you? What do I do after I find du? Divide. Why does that make all the difference? All of those were no-goes because I had to have a 1/2. And then all you had to know is forever card that a sine comes from a negative cosine and a cosine comes from a positive sine. Dun, 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 dun. U sub. Okay, where else are we going? 6? Okay. In your cheat sheet, do or have we talked about limits of piecewise functions yet? But why is this even weirder than the cheat sheet? The cheat sheet shows a greater than and a less than, and you plug into both pieces and you see if they agree. If so, it's continuous. If the derivative agrees, then the function's differentiable. But does this have greater than, less than? It's a different type of piecewise, but don't worry, we did this in our notes. There's the greater than, less than type of piecewise, and then there's the not equal to, equal to. That's what this guy is. Guys, how do we take a limit of a not equal to, equal to? Don't I have to come from below and come from above? Wait a minute, 1.9, what piece would that be? This guy? Wait a minute, 2.1, what piece would that be? This guy? Oh, so what am I doing for any of my limits? Just the top guy. If you plug in 0 over 0, what would you guys do, factor or L'Hopital's? L'Hopital's is fine. You get 2x over 1 and plug in, you get 4. The other way, you get x plus 2, x minus 2. The x minus 2's cancel out. X plus 2, 2 plus 2 is 4. Either way, the limit exists and the limit is 4. So this one is totally good. The limit exists and the limit is 4. L'Hopital's or factoring and then canceling out and then plugging in. But what extra has to be true for it to be continuous? Not for continuous. If a function is continuous, it has to be differentiable. If it's differentiable, it has to be continuous. But what needs to be true for it to be continuous? Good. F of c exists. Can I plug in 2 and get a number? Yeah. The limit as x approaches c has to exist. Oh, it does. It's 4. And they have to agree. Well, does 1 equal 4? No. And if a function is not continuous, what can it not be? Dun, 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 dun. The answer is only 1. The limit has to equal the function value, which it does not. Where else are we going? 9? Anything before 9? 7? A particle. Hey, motion, yeah? They tell me something about velocity, right, guys? That's like the first derivative. And then they tell me a position. And then they ask me for another position? Wait. What Forever Card says, if you give me the rate, and if you give me one value, I'll find the other value for you. Integration is net change. If you tell me 1, I'll find you the other one. But how would we make our integral? They want it at 1. They told me what's going on at 0. So what must my bounds be? If worst comes to worst, why don't you guys subtract? You have antiderivative of b minus antiderivative of a. Isn't it 0 to 1? If I know where it started, if I know what's going on at 0, and if I can add the change, I'll know where it's at. That's what we talked about yesterday. And I can throw in my 3t squared plus 6t. At this point, the answer is, can you plug in? And then, will you, antiderive? 3t cubed over 3 cancels out, and then I have 6t squared over 2. I'm going from 0 to 1. Plugging in 1, I get 2 plus 1 is 3. 3 plus 1 is 6. Minus, and then 0. Oh, sorry, the 2's outside. My bad. My integral was right here. 2 plus 1 plus 3 is 4 minus 0 is 6. Sorry. Have to be careful with that separation of parentheses. That was totally my. But then I saw or heard number 9. Please tell me you guys did U prime. And you knew unit circles so that you were able to make it match. Number 9. Do you guys remember the name of a function whenever they write it like this? I gave you a name in a cheat sheet. What was he called? Or I think it was in 27 Essentials. I gave you the name. Starts with an A. An ACC accumulator, yeah. Because it's accumulating area as x gets, it starts at one point and accumulates more and more and more and more and more and more. Anyway, they're saying this is the graph of f. Oh dear. Come on, snipping tool, work with me. He gets tired after a while. This one's kind of tricky because this one, they don't actually force you like they would in an FRQ, which you did in your 27 Essentials. It doesn't force you to think of how G and F are related, besides just saying, I think G is somehow an antiderivative. In an FRQ, it would force you to find G prime at some point and find G double prime at some point. To find G's, you'd have to do areas, like actual areas. To find G prime, you would take an integral, guys. Don't we just plug in? So it's going to be f of u times u prime is just 1. So G prime is equal to, G is equal to area, G prime is equal to f, and G double prime, well, his derivative will be f prime. That's how we're related. So when I see this, guess what it's the thing at? the graph of the derivative, which you guys have seen time and time again. We've only been doing questions for 2 days. It's the graph of the derivative. So when it says, which of the following values is greatest, well, there are different ways you could do it. One way is you could be thinking about areas and thinking how to make the area highest. Or you could be thinking about how this is the graph of a derivative. Where is its absolute max? If this is g prime, g is increasing for this entire time. Why? Because the g prime values, the f values, are above, are positive on 0, sorry, from -2 to 1. And then they go below. So g prime is positive, then g prime is negative. Because f is positive, then f is negative, which means g is increasing this whole time, and then he starts decreasing. Where's the only natural place for this to be at its highest value? Right there. It's increasing, it's increasing, it's increasing. Sometimes faster, sometimes slower. Sometimes faster, sometimes slower. But it's increasing all the way up until here, and then it dips into decreasing. That's a relative max. That's one way. Another way of thinking about it is if G is area. Guys, isn't this a positive area? And isn't this a positive area? So you're adding and you're adding and you're adding and you're adding, but what do you start doing with area as soon as you go past this? You start subtracting. So you have to stop before the subtraction. This will be the highest accumulation or the greatest accumulation. So whether you're thinking about area or whether you're thinking about behavior, both ways say 1 at 1 is the highest. So G of 1 will be the highest. What else do we have, guys? 18? Anything before 18? 13? They give you a clue. You could do this a few different ways. The way I would have done it is a little different than the way they would have done it. They went ahead and said, literally, who is this guy? Oh, no, let's just go plug him in. Plug him in there, and then plug him in there, and we'll get our function. Derive. That's one way. The other way is that you could have actually done a little chain rule thing, how the derivative of f of g is f prime of g times g prime. You could have also done it that way. That would have been your first derivative. And then you would have had to say, who's f prime? Well, f prime is 2x plus 2. So to finish this off, you would have had to plug in. So it would have been 2 times ln of x plus 2 all over x. You could have done it with a quick little, I don't want to make a big old nasty function first. I just want to go ahead and do my chain rule. Derivative of the outside, keep the inside, times derivative of the inside. Go figure out who f prime is, and then plug in chug. Plug in ln, and then divide by x. But this way works too. You could have also done it where you bring down, for derivative of ln of x squared, bring down the 2, make it a 1 times u prime, plus 2 times ln of x is 2 times 1 over x. You could have made a common denominator, everybody's over x, and then you have the exact same answer. But it depends on your brain as to which one's safer and which one's, I don't know, the way that you should probably tend to go. I'm going to 18. Anything else you want to stop me on? 14? Gives me a graph of a derivative, yeah? Oh, nope, a second derivative. The polynomial function f has selected values of its second derivative. Which of the following must be true? Which of the following must be true? Guys, second derivatives tell me about increasing, decreasing of, let's see. F prime would be increasing, f would be concave up. Here, f prime, oh, not sure if I necessarily know. F prime is constant, f is, that's like an in-between. This one, f prime is decreasing, and f is concave down. And that's only at 2 and at 0. I'm not exactly sure what's all happening in between, though. I just know that there is a pip somewhere. A pip, a second derivative equal to 0. There's a pip somewhere in between. And then I know once again f prime is increasing, f is concave up. Okay. Polynomial function means it's continuous differentiable. All of these will be smooth turns, smooth transitions. But when they start talking about f is increasing on the interval 0 to 2, I know it's increasing at 0. I know it's increasing at 0. But do I know what's happening after 0? Not actually. And to be honest, I see a decrease and a decrease on average. I don't know exactly. It might increase and I don't know exactly what's going to happen, but I know it's increasing at 0, decreasing at 2, and all I see is average decreases. So I don't think I can say, wait a minute, who's increasing and decreasing anyway? Is it F or F prime? Oh, I know nothing about F increasing or decreasing. I don't know if F prime is positive or negative. I just know what F prime is doing. So I have no idea what F is doing as far as increasing or decreasing. F has a local max at 1. F prime might have a local max at 1, but if stuff changes, it might not even have an F prime. Nope, forget that. Not F. I don't know. The graph has a point of inflection at 1. Oh, yeah. The concept changes. What's happening at 0.9999999? 1 from a... No. All I know is what was happening a long time ago at 0 and a long time ago at 2. This is not the same where I know it's been split up by pips. There could have been a pip somewhere like positive a half. There could have been another pip there. So yeah, it could be positive here, but then it could have been negative and then negative, and maybe nothing changed. Maybe nothing changed at 1. So I don't honestly know. All I know is there's a pip, and somewhere there's a positive here, and somewhere there's a negative there. I don't know for sure that 1 is the point of inflection, but I do know somehow there has to be a concavity change somewhere. I can't tell you where. It's a table. All I know is very loose information, but it's enough to say somewhere there's a change in concavity. I just don't know exactly where. Going to number 18, because we've been waiting a while to get there. Okay. There's a tendency for all of us to kind of just focus on K and be like, who the heck is K? But if I were you, I would focus on the word tangent. Because tangent, don't I know to make a y minus f of a? Now, they didn't tell me very much, but they did tell me that this dude, who's a line who can be rewritten as y equals negative x plus k, somehow came from this guy. That made this. Can anyone tell me the one thing I can know for sure? I don't know A, I don't know f of A, but what do I know? I know the slope is negative 1. So I know f prime of A equals negative 1, and I have my f that I can take the derivative of 2A plus 3 equals negative 1. Subtract 3, negative 4, 2. I can find my A by saying, oh, his derivative has to equal negative 1, because I know the slope. Well, wait a minute. If I know him, can't I plug back in and say, oh, f of negative 2, f of A is equal to 4 minus 6 plus 1, which would be negative 2 plus 1, negative 1. So now I know my A, now I know my f of A, and I know my slope. I can build this tangent line myself. I didn't even need that clue. So y minus negative 1 is equal to negative 1, x plus 2. And then I can actually say y is equal to negative x minus 2 plus 1 minus 1 minus 3. Who needs to go in that K spot? A negative 3, of course. Kiddos, I'm going to hand you the first FRQs. There are 6 total, but there are 3 in this packet. These are calculator FRQs, and it even says 45 minutes on here. Here's the struggle. We cannot possibly finish questions tomorrow unless you attempt the FRQs, 45 minutes, no notes, no forever cards, no anything. But then you must go to the answer key and try to give yourself a score out of 9. Okay? A 0 out of 9, 1 out of 9, 2 out of 9. You have to grade and come tomorrow with already having thought through the answer key. Sound good? All right, come here. See you guys later. Sorry, coming. Oh, there's 2 here, but they're stuck.
Thank you. Thank you.
Okay.
Thank you.
Hey, don't give up on me. Come on. You're welcome.